Dear students, in the previous session we learned something about what are alcohols, how are they classified, and what are the methods of naming them, and we learned something about the preparation of alcohols. We learned how to prepare monohydric, dihydric and trihydric alcohols. Now preparation is over. Imagine in a table in the chemistry lab we have three types of alcohols: a primary alcohol and a secondary alcohol and a tertiary alcohol. All of them look colorless. Your teacher is asking you to find out which is primary, which is secondary and which is tertiary. How will you do that? You can't drink and find out, because alcohols are sometimes dangerous too. As you know, methyl alcohol and ethyl alcohol are differing only by a CH2 group. But methyl alcohol is deadly poisonous, and ethyl alcohol is available in the beverages. So never try tasting any of the chemical without knowing the background or the chemical nature of the substance. That is a wrong strategy. So what to do? We can't identify the particular alcohol by looking at the color, because all of them are colorless liquids. And best method is to go with the chemical method of detecting. And today we are going to begin our session with what are the methods of distinguishing primary, secondary and tertiary alcohols. So the distinguished part will give us a very clear-cut information about the type of alcohol. For that, we are going to proceed with the Lucas test. Before going to Lucas test, we should understand with what Lucas is going to distinguish between primary, secondary and tertiary alcohol by adding some chemical. So that chemical, it's not a chemical, it's a combination of two of the chemicals. So he is naming it as Lucas reagent. What is that? He is using anhydrous. Anhydrous, from the word you can understand, it doesn't carry water. Anhydrous zinc chloride, and in the presence of a concentrated hydrochloric acid. This is called as the Lucas reagent. Anhydrous zinc chloride and concentrated hydrochloric acid is now going to give us an input how to distinguish these three types of alcohols. So how are you going to proceed now? Let us consider the three types of alcohol. To start with, let me go with one primary alcohol. Primary alcohol, the simplest one, CH3, CH2, OH. As you know, boys, we have learned in a primary alcohol, the OH attached carbon will carry two alpha hydrogens. So it will be CH2OH in nature. And secondary, I am giving you another example, CH3, CHOH and CH3. Look at this particular alcohol. CHOH is the structure. Two alkyl groups are attached with a carbon bearing OH group. The next alcohol is tertiary. It has COH as the structure. All the three sides I am attaching with a methyl group. So three types of alcohols are with us. I hope you are familiar with the naming nowadays. We learned the basics of IUPAC nomenclature. There's two carbon atoms, so it is a single bonded compound, ends with OL, so ethanol. Here it is second carbon bearing the OH group, it is 2-propanol. And here it is propane chain and second carbon OH group and second carbon methyl group. So prefix 2-methyl propane 2-ol. That's how we name them. Hope you are familiar with IUPAC names and all. Now let us go with this reaction. The ethyl alcohol molecule carries one OH group. We are going to treat with hydrochloric acid from the Lucas reagent, and you can have a clear guess from the right hand side of this ethyl alcohol OH group and left hand side of hydrochloric acid hydrogen, they are going to react. Mostly in chemistry, we should understand one of the reactants right hand side and another reactants left hand side will easily go for reactivity. And writing the equation and products are very simple for you. So you follow this strategy. So ethyl alcohol is right hand side and hydrochloric acid is left hand side. So I am going to remove this as a molecule of water. That water is taken away by anhydrous zinc chloride. It is not having water, so it will remove the water. After the loss of water, what is remaining? A chlorine in the place of OH group, the chloride ion will get attached to it. So the product is CH3, CH2Cl, ethyl chloride. That is ethyl alcohol has been converted into ethyl chloride. Or IUPAC name chloroethane. The same way here also hydrochloric acid you react, the molecule of water will be removed and the product formed is CH3, CHCl and CH3. So this is 2-chloropropane. And the next one, tertiary butyl alcohol, similar manner it reacts hydrochloric acid and the tertiary butyl alcohol on reaction gives you tertiary butyl chloride. Only difference in all these things are, you look at that, in the place of OH group, Cl is going to be substituted. That is a reaction, that is a Lucas test. And now you may be asking a question, how are you going to distinguish with that? So when performing this particular test, the scientist Lucas found that this particular compound which is coming out of a tertiary butyl alcohol formed turbidity immediately. What is the meaning of turbidity? The alcohol taken after adding a Lucas reagent, immediately the solution becomes turbid. Maybe I can quote a simple example. When you try to open a Pepsi bottle, before that if it is shaken, then you can see a combination of a gaseous layer on the top and the liquid in the first layer will be a turbid layer. So that turbidity will be there immediately with the tertiary alcohol. And for secondary alcohol, it may go 5 to 10 minutes. Within 10 minutes, it will give a turbidity. But say primary alcohol will not react at room temperature. Only on heating, it will form the turbidity. So, 3 test tube is taken. One of the test tube primary alcohol, second test tube secondary alcohol, and third test tube tertiary alcohol. With those test tubes, he is going to add a Lucas reagent in every test tube. And the turbidity immediately formed substance is going to be tertiary alcohol. And next after 10 minutes is secondary, and that one is primary. So this is the simple way and can be asked in a 3 mark 2 as an important question, or you can mention in your textbook as PC that may be given as a problem, clue. So the reactivity, they say tertiary alcohols will be more reactive with the Lucas reagent than secondary than primary. This is Lucas test.
Quantity of primary, secondary and tertiary alcohol in 3 different test tubes labeled as A, B and C. Using the dropper, add a small quantity of Lucas reagent into tertiary alcohol taken in test tube C. Shake the test tube well. Tertiary alcohol reacts instantaneously with Lucas reagent to form alkyl chloride, which being insoluble results in cloudiness in the solution. Then add a small quantity of Lucas reagent into secondary alcohol taken in test tube B and shake the test tube well. Secondary alcohol reacts in about 1 to 5 minutes with Lucas reagent to form alkyl chloride, which being insoluble results in cloudiness in the solution. Now add a small quantity of Lucas reagent into primary alcohol. Warm the test tube on a water bath. On warming, primary alcohol reacts with the Lucas reagent to form alkyl chloride, which being insoluble results in cloudiness in the solution.
To distinguish three types of alcohol, we learned the Lucas test. The next one will give an interesting appearance of different coloration with the different alcohols. So that is a wonderful test called as the MEYER'S test. In MEYER'S test, we will be identifying primary, secondary and tertiary alcohol with the color. How? Let us go with the same example. Primary alcohol CH3, CH2OH. One example. Secondary alcohol I have taken CH3, CHOH and CH3. That is isopropyl alcohol or 2-propanol, secondary alcohol. Tertiary alcohol is tertiary butyl alcohol, or I can say 2-methyl 2-propanol. So three types of alcohol we have taken. And in the problem they will give this way. It may be a problem type of question. Compound A, they go with the 4 steps. Compound A on treatment with the red phosphorus for iodine gives compound B. That again on treatment with the AgNO2 silver nitrite to give a compound C. That on treatment with the nitrous acid HNO2, or they may give it in this form, sodium nitrite and hydrochloric acid combination to give compound D. And compound D on treatment with the KOH, potassium hydroxide, gives different colors. Maybe one of the compound may give a red color, one compound may give a blue color, the other compound may remain as a colorless. This is how they coin a problem. And if you properly go with the particular alcohol, whether it's primary, secondary or tertiary, then with the color the ending product will be very fine. If not, you will be taken into another path, will be misled, and your product will be different. So you have to be careful. So all that clues you will be getting. Step 1 for all these three, let us add phosphorus for iodine. And in a simplified manner, phosphorus for iodine, instead we add HI, hydroiodic acid, for your easy understanding. You know what is going to happen? This side, this reactant right hand side and that reaction left hand side will be reacting. Hydrochloric acid, water will be removed and iodine gets added. So the resultant product CH3, CH2I. So A compound ethyl alcohol, B compound is iodoethane or ethyl iodide. If it is taken as a primary alcohol. Let us go with the secondary alcohol. Secondary alcohol, the alcohol taken is 2-propanol. With that same phosphorus per iodine, a molecule of water is removed and the product is CH3, CHI, CH3, isopropyl iodide or 2-iodopropane. So if secondary alcohol is taken as A, then B will be 2-iodopropane. And you can have an easy guess for a tertiary alcohol. Similar reaction only, we are adding HI, molecule of water is removed, and the product will carry as and iodine here. So it is tertiary butyl iodide or 2-methyl-2-iodopropane is the IUPAC name. So next step we are adding AgNO2, silver nitrite. AgNO3 is silver nitrate, AgNO2 is silver nitrite. Now we are adding silver nitrite only. With this you add, and a similar way of dealing. You see right hand side of this, left hand side of this going to be removed as AgI, silver iodide. NO2 group will get added. So the next compound formed is going to be nitroethane, 2 carbon atom, single bond ethane. That is going to be C compound. And here again the same reactivity we are treating with the silver nitrite, AgNO2, second step, and the same process. The learning chemistry is very easy. Look at that, AgI is removed and the product is CH3, CH3. In this place the NO2 group is added. Naming is also easy. How? 1, 2, 3 carbon, so propane, second carbon nitro group, so 2 nitropropane. And similarly we go for tertiary butyl also, AgNO2. AgI is removed, NO2 group is added, CH3C, CH3, CH3, and the NO2. Till now no confusion, you can see 2-methyl-2-nitropropane as a product. Similarly, up to this, all these primary, secondary, tertiary alcohols reactivity with the reagents were quite good and the same. Similar way of substitution. But now comes the difference. What is the difference? In a primary alcohol, you closely see the CH2OH. There the OH attached carbon is called as an alpha carbon. That alpha carbon has how many hydrogens? 2 hydrogens. So primary alcohol will carry 2 alpha hydrogen, whereas OH attached carbon is alpha, here only 1 hydrogen. So secondary will carry only 1 alpha hydrogen, whereas in tertiary no alpha hydrogen. This is the area you have to understand carefully. So primary, secondary, tertiary are differentiated with respect to number of alpha hydrogens. And 2 alpha hydrogen, 1 alpha hydrogen, no alpha hydrogen. So till now we were not talking about the alpha hydrogen. Now when you are treating the third step with this, sodium nitrite and hydrochloric acid, it will release HNO2, nitrous acid. This HNO2 I am writing this way, O double bond N OH. Oh no, that is HONO. And the same reaction I am doing here also. I am adding HONO. And this way, you just closely look here. Since he is having 2 alpha hydrogens and this oxygen and that hydrogen will react, by the laws of water molecule, this double bonded NOH group will get added here. So look at the product carefully. CH3, C double bond NOH and NO2. This is an oxime, or they say nitrolic acid. And here you can see the molecule of water can be removed this way. You should understand. Here I am writing HONOH. Here HONO. The reason is I am trying to remove the water. That's how in chemistry you should write the reactants so that removal of the product is easily probable. Next one. After laws of water molecule, you can see this molecule CH3 carbon single bond N double bond O. This gets attached here, and the NO2 group here, and this is CH3. This molecule is called as nitroso group. This group is called as nitro group. So we are getting nitroso group. So if you closely see the number, 2-nitrosopropane. That reactivity I am trying HONO or ONOH. Anyway I am trying, it is not possible at all because there is no presence of alpha hydrogen. So tertiary cannot proceed further. It will remain as a colorless liquid. Whereas these people will go for the next step formation. The primary I am adding KOH, potassium hydroxide, and there is a nitric acid group, is the basic group. What happens is there is a breaking of bond, K plus OH minus. In the place of this H plus K plus will get added. So the resulting product will be CH3, C double bond N O K plus O minus, and NO2 is remaining as such. So this particular substance, while forming, the whole solution will get converted into red color. And this substance will remain as a blue colored substance. And this will not react, so it will be available as a colorless liquid. So it's a very good distinction between primary, secondary and tertiary. And imagine if it is asked in a problem question, they will give a molecular formula C2H6O, an organic compound with this molecular formula C2H6O. Then you have to guess the clues related to that. Finally, after all these steps they may give, the compound gave a red color, and then it is a primary alcohol. Or else we can go for this formula C3H8O. So for C3H8O I can write a structure the other day we learned. It can be 1-propanol or it can be a 2-propanol. 1-propanol is having CH2OH, so it is a primary alcohol, and 2-propanol is a secondary alcohol. So if you are following closely the Victor-Meyer's steps 1, 2, 3, 4, and finally the A compound they give a clue as a red color, it means it is 1-propanol. If the A compound they say finally it gives blue color, then it is 2-propanol. So once this idea is understood, you can able to distinguish between primary, secondary and tertiary. Next idea, we have to learn about the physical properties of alcohols. What are physical properties? How do they exist in the nature, and also how do they respond to the action of heat? All that we have to learn, whether it's soluble or not. Yes. So now most of the alcohols, the lower members are liquids, and when the molecular mass, molecular weight increases, they become waxy solids. You would have seen the alcohol's nature. Methyl alcohol is a liquid and easily evaporable, and nowadays sanitizers you can see the ethyl alcohol's presence, and after applying to the hands they slowly evaporate out of our hands. That is, they are volatile liquids, easily evaporable. And doctor's injection, you can see isopropyl alcohol before injection, he applies and you can feel the chilling effect in your body when it is being applied, even the sanitizers, and for example some of the perfumes. And that reason is they gain heat energy out of our body and they evaporate. And that while removing the heat energy out of our body, they give a chilling effect to ourselves, our skin. So that's why the lower members, and when the molecular mass, number of carbon atoms increases, they become waxy solids. And the second important thing is they are showing high BP, and boiling point increases. And what are the reasons? They have a new capacity, that is, they can go for intermolecular hydrogen bonding. And we have a big puzzle about water. What is it? How can you form water? If you take hydrogen and oxygen, you form water. Now hydrogen is a gaseous molecule and oxygen is also existing in gaseous state, but the formed water goes for liquid state. And if this is not happening, there is no presence of water, there is no life in the earth. Almost 3/4 we are covered with water only. And this wonderful behavior of this is because of intermolecular hydrogen bonding. That is, one of the water molecules, oxygen, since it is more electronegative, it will go and join with the neighboring water molecules, hydrogen, so because it is little electropositive. So this make water molecules in a gaseous form to come closer, they will get connected and become liquid. That is called as intermolecular hydrogen bonding. This intermolecular hydrogen bonding is the reason why we have water existing in a liquid state, and our protein molecules and biomolecules inside our body, our sugar, all of them are going for intermolecular hydrogen bonding. And the same behavior is also available in alcohol, because we learned alcohol molecule is similar to that of water, where one side hydrogen, other side instead of hydrogen we go for R, that's all. So ROH is the group. So they go for intermolecular hydrogen bonding, and if you take the molecule called as butane. Butane, I write the molecular formula CH3, CH2, CH2 and CH3. The molecular mass is 58 and its boiling point is 272.5. Similarly, I go for one more molecule, it is propanale. Propanale is having CH3, CH2, CHO. The reason why I am adding A here, this is an aldehyde group. Aldehyde starts with the A. So this is one propanale. And this molecule also, the molecular mass is 58 and it is showing 322 as a boiling point. And you go for the next molecule of methoxyethane. Methoxyethane, the molecular mass is 60. CH3O, CH2 and CH3. This shows 283.8 as a boiling point. And if you go for the next molecule, 1-propanol or propane 1-ol, and we learned the formula of these compounds CH3, CH2, CH2, OH, and it is also having similarly molecular mass 60, but the boiling point, if you look closely, 370.4. I go for 2-propanol, 2-propanol or propane 2-ol, CH3, CHOH, CH3. Its boiling point is 355.5 and molecular mass is same, 60 only. And all of these people are having same molecular mass, but look at the boiling points are differing. And here again a little difference only, two difference only. There a drastic change. Let us consider only these two people. One is butane with almost same molecular mass with 272.5, and 1-propanol is with 375, almost approximately 100 difference of boiling point. The reason is this is only an hydrocarbon, whereas 1-propanol is an alcohol. Alcohols, as I told you, they can go for intermolecular hydrogen bonding with the neighboring molecule. So because of that, what happens is they will have more attraction, intermolecular attraction. You have to supply more heat energy to break the attraction and to make it to go for a vapor state. So obviously the boiling point will get increased for the alcohols. This is because of intermolecular hydrogen bonding. And next one, when we comparing primary, secondary and tertiary, primary's boiling point is greater compared to secondary and tertiary. What is the reason? You look at these examples carefully, where this is a primary alcohol, this is a secondary alcohol. So primary alcohol, they go for a linear chain. Obviously their the intermolecular hydrogen bond formation capacity will be more. So that is why primary will show higher boiling point too. And next one, how do they dissolve? So solubility. How to explain solubility? The same strategy we can adopt. They go for intermolecular hydrogen bonding. For example, we take a molecule of water. So water is existing like this. And I go for an alcohol, maybe ROH. And here another alcohol like this. Or ROH in between a water molecule. Then there is a big question arises in front of us. Alcohols are coming under organic chemistry. Water is an inorganic molecule. How come alcohol is soluble in water, whereas petrol, diesel are not soluble in water? They are immiscible. How can these alcohols are soluble in water? They say when you check these molecules, they can go for intermolecular hydrogen bonding. You have to check their capacity to link with the neighbor. So that, look at this oxygen of the alcohol is electronegative and goes for hydrogen bonding with the neighboring water's hydrogen, because here also oxygen is electronegative, hydrogen is electropositive.
For example, the boiling point of ethanol is considerably higher than that of methoxymethane or propane. Although all the three substances have very similar molecular masses. Both alcohols and phenols can participate in intermolecular hydrogen bonds due to the presence of the polar hydroxyl group. Thus, alcohols and phenols have higher boiling points than ethers or hydrocarbons, which cannot participate in hydrogen bonding. Alcohols and phenol can both form hydrogen bonds with water, and so both are water soluble.
Next, let us learn about chemical properties of alcohols. How do they go for chemical behaviors or chemical reactivity with other reactants? That is our next idea. To start with, let us talk about the nucleophilic substitution reactions of alcohols. So what are nucleophilic substitution reactions? Yesterday we learned a nucleophile will come and one nucleophile will get substituted. SN type of reaction, and yesterday again we learned SN1 type of reaction, SN2 type of reaction. SN2 type of reaction we talk about primary alcohols, and SN1 type of reactions mainly we talk about secondary and the tertiary. And similarly, let us go with this. And in an alcohol molecule, for example, CH3, CH2, OH, this particular alcohol OH group, since it is carrying, oxygen atom is carrying two lone pairs of electrons, it can behave like a basic nucleophile, and in the presence of an HBr, hydrogen bromide, their bond will get heterolytic fission. Therein hydrogen gains a positive charge and bromine gains a negative charge. And here the same thing like yesterday, we are going to treat an alcohol, primary alcohol with hydrogen bromide, where Br minus is a nucleophile and this OH minus will leave the place, Br minus will get attached. Then the required product will be bromoethane or ethyl bromide. This is what is our expectation. First step, what happens is, this lone pair of electron over the oxygen will be donated to the H plus ion. There it will give the lone pair. Because of that, the oxygen will attach one more hydrogen and gains a positive charge. So this particular group has to leave the place as H2O in the next step, minus H2O, and Br minus ion is available, that will go on to occupy that area. So the final product form is the CH3CH2 Br, ethyl bromide. So this is a SN2 type of reaction. So the OH minus will leave the place and Br minus will go and join to form ethyl bromide. Suppose we go for a tertiary compound, tertiary butyl alcohol, CH3, replace the CH3 group and OH. How this tertiary butyl alcohol will react with the same HBr? Similar reaction only, the bond breaks here heterolytically, H plus and Br minus, and this Br minus is going to attack. Before that, as usual, the one of the lone pair will be donated for the hydrogen, and because of the lone pair donation, there will be a new bond with the hydrogen and oxygen will get a positive charge. And now the whole H2O molecule has to leave the place. Now if you closely see, the carbon is losing its electron, so he is going to get a positive charge. So these two electrons will go over oxygen to make water neutral. Then the resulting product is a formation of a carbocation, which is sp3 hybridized and planar in nature. So carbon carrying positive charge, we call it as a carbocation. This is the next step formation. And from this step, what is going to happen there is a possibility of deprotonation. That means I write it like the CH2 and the hydrogen. One of the hydrogen will be removed as a H plus. That's why they say deprotonation. Proton, this particular H plus carries only one proton, no electron. So we can call it as proton is being removed. That's why it's called as a deprotonation. So this pair of electron, if it is coming here, the double bond will be formed and the positive charge will get neutralized and you will get a compound CH3 carbon CH3, a double bonded CH2. The name of the compound is isobutylene. This isobutylene can be written in IUPAC. Look at that here, 1, 2. So we have to add ene. And the position of the double bond is 1, so I am adding prop 1 ene. And the methyl group is at the second position, so we have to include a prefix 2-methylpropanene. This is the compound. This compound again goes for reaction with the HBr, and the bond breaks here, and you will get hydrogen added here and the bromine added here. We learned yesterday about Markovnikov rule also. Then you get CH3, 3 sides to CH3 group, and bromine here. You get tertiary butyl bromide. The same thing will happen in this place also. Since the carbocation is available, and with that carbocation, the Br minus ion can easily go and join, and thereby addition of this Br minus addition So we'll give you this tertiary butyl bromide. So you can go in two methods. From the carbocation goes for an deprotonation process. The deprotonation process, formation of isobutylene or 2-methylpropionine, or else from the carbocation directly you can go for bromine. From this step it will go with the reaction with the HBr. So this is how a tertiary butyl alcohol will go for treatment with the HBr to give an tertiary butyl bromide. What are the other methods of preparing this alkyl halide from alcohol? First method we have learned just now. What are the other methods? You can treat it with the PCl3, phosphorus trichloride. Example, I can take this molecule CH3, CH2OH, ethyl alcohol. Ethyl alcohol we are going to treat with the phosphorus trichloride. So this I am writing with a small change. Hydrogen here, and oxygen is carrying a lone pair of electron, and chlorine is electronegative species. So what happens? It will take the electron of phosphorus and go as a Cl minus. Will get removed. And this molecule, PCl2 molecule, will be attracted by this oxygen. That means the lone pair will be donated to this PCl2 molecule. So you will get a new compound, an intermediate CH3, CH2, OH, that since it has lost a pair of electron will get positive charge, and then phosphorus with the 2-chloride. The next step, this hydrogen will be removed as a H plus, and this pair of electron will go here. The whole molecule here will be lost as a POCl2 minus, and in that place only this chlorine Cl minus ion will go and attack to form CH3, CH2Cl. So this is another way of converting OH group into chloride. What are the other methods? We can go for even methyl alcohol or ethyl alcohol and treat with the thionyl chloride SOCl2 in the presence of pyridine. And during this reaction, I can make it easy for you. The bond breaks here. This molecule I can write as Cl, SO and Cl. The right hand side is HCl, and in between sulfur dioxide, and CH3 will add with the Cl, we will get a methyl chloride form. So this is the easiest method. Pyridine's presence is required for this reaction. So thereby we can convert the OH group into a chloride group. Then the ethyl alcohol will become ethyl chloride, methyl alcohol will become methyl chloride. Now we learnt about substitution reactions of alcohols. Let us learn little about elimination reactions too. So the second one we are going to talk about elimination reaction. What are elimination? From one of the carbon we are going to remove OH group, from the neighboring carbon we are going to remove hydrogen. So literally speaking, we are going to remove H2O. That is removal of water, we call that as dehydration. For dehydration, main requisite is an agent, dehydrating agent. It can be a sulfuric acid, or it can be an alumina or anhydrous zinc chloride, or it can be a phosphoric acid also. All these people have the capacity to remove the water. An example of ethyl alcohol. Ethyl alcohol formula is CH3, CH2OH. This is an example for a primary alcohol. So primary alcohol will go for elimination according to E2 mechanism. We will learn that. That means I am writing the same molecule ethyl alcohol this way, CH2H, CH2O, Oxygen carries 2 lone pairs of electrons. When we are reacting with the sulfuric acid molecule, I can write HOSO3H. That is, this bond will break. Sulfuric acid has the ability to give H plus ion. So now this lone pair of electron will be donated for this H plus ion. Then there will be a new product CH2 here, O with the 2 hydrogens and they will gain a positive charge. As usual, like last step, we can remove this as water, and this hydrogen has to go as a H plus, deprotonation takes place, and this pair of electron will come in between CH2 and CH2. So the final product will be CH2 double bond CH2, that is ethylene, or otherwise called as ethene. Now it is a process of removal of water. It is called as dehydration, and it is otherwise known as the elimination reaction. Finally it gave us an unsaturated compound, a double bonded compound. This is with the primary. Let us go with the tertiary, and for tertiary let us take a tertiary butyl alcohol. Step by step it will go for the process. First step, as usual step only, we are adding sulfuric acid HOSO3H, and the bond breaks here, H plus SO3H minus, and this pair of electron will be donated here. That hydrogen will get added with oxygen, so oxygen will get a positive charge, CH3 and CH3 O with the 2 hydrogen and a positive charge. Next step, this water will be removed. It will go with the electron of carbon, and this electron will go, the positive charge will get neutralized. Thereby the carbon will be losing an electron, will get a positive charge. So there is a formation of a carbocation. We learnt in the last reaction also. So this is how that the E1 mechanism will be carried out. E1 elimination, first order. This is elimination bimolecular, unimolecular, and here there is an intermediate. That intermediate is a sp2 hybridized carbocation. The next step, one of the hydrogen available in this position will be removed as a H plus. This is the next step, deprotonation. And this bond will get shifted here. Then there will be a formation of a new double bond. And we learned in the previous reaction also, this is called as isobutylene or 2-methyl-propionine. So this is how elimination reaction is carried out in alcohol. You have to understand, primary will go for E2 type of elimination reaction, and tertiary will go for E1 type of reaction. Zaitsev rule. So what is the Zaitsev rule? In a particular reaction, water molecule is being removed, that we call as dehydration. Within the molecule it happens. Thereby there is a formation of double bond, we learned in the previous content. The formation of alkene. Zaitsev is coming with the idea, if there is a possibility of more than one way of water removal and double bond formation at different location, then we have to adopt Zaitsev rule. That means with one example you can understand better. I am writing this molecule, and let us learn CH here, OH and CH3. If you closely see this molecule, let me number from right to left. So 4 carbon atoms, the route towards a bute, single bonded, so it ends with the N, butane, and it is an alcohol, that too is in the second position, so remove this E and add OL, so it is butanol. And in the third position there are two methyl groups, I can say 3, 3 dimethyl butan 2-ol is the actual IUPAC name for this compound. Why we have chosen this particular compound? This compound is also going for dehydration. It's a well-known story only. We are going to add a sulfuric acid concentrator and write the molecule HOSO3H, sulfuric acid. And the bond between oxygen and hydrogen is weak, so it will break heterolytically to give H plus ion. The bond goes here. HSO3, HSO4 minus will be the product. Now the oxygen carries two lone pairs. One of the lone pair will be donated for this H plus ion. Like in the previous test step we have learned, this hydrogen will join here by using the lone pair, and then the oxygen will get a positive charge. This is what we learned. And as usual step only, there will be the removal of a water molecule. This also we learned. When the water is removed, this particular carbon is losing its electron. So he will receive positive charge. So carbon getting positive charge, we call them as a carbocation. Now the molecule of H2O is being removed, and because of that this carbon receives a positive charge. And if you closely watch, this particular carbon is CH in nature, so it is a secondary carbocation. To this carbon, in the beta position, there is one hydrogen available. So what is the next step? One possibility, this hydrogen will be removed as a H plus. Because of that you will get one of the compound, as such I am writing CH3 carbon, CH3, CH single bond CH2. Since the hydrogen is going without electron, it goes as H plus deprotonation. This pair of electron can come here at the bond there. So if this is getting shifted here, then obviously the positive charge will get neutralized. Then you will get a new bond, a double bond will be formed. If you closely look at the name of this compound, 1, 2, 3, 4, 3, 3 dimethyl 1-butene or but1-ene is the name. This is one possibility. The probable product is very, very low. Minor product, only 3% yield. Then what is the other possibility? Let us go for shifting. That means what? They call it as methyl shift. Methyl shift, what is going to happen? The CH3 group with the bond, it is traveling to this secondary carbocation and get attached. And because of that, the positive charge will get shifted over this carbon. And that we can write this way, CH3 carbon, CH3, and here it gets a positive charge, and here CH, CH3, and here CH3. So this is the next molecule. So methyl has got shifted. Because of the methyl shifter, this carbon receives a positive charge. Now if you closely see this carbon, it is C plus in nature, that is a tertiary carbocation. In that tertiary carbocation also, we have to see how this hydrogen gets removed. There is one possibility of losing this hydrogen as H plus, then the double bond, if suppose I am removing this as a H plus, and the bond gets shifted here, and the positive charge will get neutralized. There is one possibility, CH3, C, CH3, double bond C, CH3 and CH3. This is one possibility. And this molecule you can write this way also. CH3 carbon, double bond, CH3 carbon, CH3 and CH3. If you want to give the name for this compound, you can start from here also. 1, 2, 3, 4. It's a symmetrical molecule. And in the second position, there is one methyl group, and in the third position, there is another methyl group. And double bond is in the second position. We can give 2, 3 dimethyl butadiene is the name. And here the hydrogen gets removed from this position. Now there is one more possibility. This molecule I am writing this way, CH2 and the hydrogen. And from this beta position that hydrogen gets removed, H plus, then this bond gets shifted here. This is the another possibility. Then you can write this becomes CH2 double bond carbon, the positive charge will get neutralized, and CH3 carbon, here one CH3 group and here another CH3 group. This is the next molecule. Let us go for the naming here. 1, 2, 3, 4 carbon. In the second position a methyl group, in the third position a methyl group. 2, 3 dimethyl but1ene is the name of the product. So according to Zaitsev rule plays a vital role only after the methyl shift is over. There are possibilities of 2 carbocations, so those are tertiary in nature. In that tertiary carbocation, out of the secondary and tertiary is more preferred. In the tertiary again, the compound with the more number of alkyl substituent is preferred for the alkene formation. So that this may be 64% probable, the maximum yield, and this particular product will be 33% only probable. So Zaitsev rule gives a clear indication of intermolecular dehydration, wherein the possibility of alkene formation where the double bond position can be formed in different locations. If you closely see, here a double bond is present in first position, and in this position this side with a less number of substituent, and here more number of substituents. So this is the most preferred and probable